Okay, we've got another video. Today we're going to be doing Specialist Math Stage 2, the last two chapters of Chapter 2. In this video I'll be covering rational functions, absolute value functions, and graphs involving the absolute value function, or ABS, on your calculator. Alright, so we start with rational functions. The rational functions generally involve a division between two functions. So I could say f of x equals g of x on h of x would be a rational function. All right, it will have zeros when g of x equals 0. The idea of like the division of two functions. Doesn't matter what the outcome of h of x is, you can't divide and get 0, but you will have vertical asymptotes. When h of x equals 0. All right. So we're going to look at a particular subset of these. We're going to look at the form of the linear divided by linear. So the idea is something like y. So let's talk about linear over linear. That can be expressed as in the form of y equals ax plus b over cx plus d. Or you can convert that into something along the lines of, and I'll just write this in terms of completely different symbols, a plus b c x plus d, where they're not the same anymore, but we carried out some sort of division to get this. We're going to go through how to do this, and this is an interesting form because this one we can determine, this form is useful to determine, can determine horizontal asymptotes. I.e., what does y do? What does y approach when modulus of x goes between goes to infinity on either side? So there should be a pattern, and this form helps us do that. So if this denominator becomes very large and this goes to 0, and we end up with a, that's basically what we're going to discover. So let's have a look at these. All right, so consider the function y equals f of x. Discuss behavior of the graph near these asymptotes. Find the axis-intercepts of that. Sketch and graph the function. All right, so we're going to carry out, and you can actually see, I'll do it. We can do it together. You can follow along with the example as you go through. All right, so example A, f of x equals 2x minus 6 over x plus 1. Now the idea is if you want to turn it into this second form, this form here, express the numerator in terms of a multiple of the denominator, even if you have to add or subtract certain values. So I'll do that in the next line. So if I wrote it as 2x plus 2 minus 8. See, I haven't changed anything. It's still minus 6 because 2 take 8 is minus 6. But what I've done is I've turned this into two lots of the denominator. So now I'm going to break that up into two parts. And I might as well just factorize it while I'm here. Okay, you see what I've done there? Now I can cancel those out, and I can express y, or f of x, as 2 minus 8 x plus 1. All right, so let's have a consider the following. All right, so we need to talk about asymptotes. All right, so vertical asymptotes. Will occur where you've got basically x plus 1 equals 0, the denominator, and so thereby x equals minus 1 is a vertical asymptote. The horizontal asymptotes all right, so as x approaches infinity, what happens to this? Well, if you've got positive infinity, then we approach, y basically approaches 2, and for x approaches negative infinity, and in this case actually approaches it from below, and the other case I believe it actually approaches from above, because if you have a minus there, well that would actually turn that whole thing into a plus. So if you have a big negative number on the bottom, well minus a divided by big negative number is small positive number. So it approaches 2 from above, but also still approaches 2. Right. So all right. So let's draw this and we'll see. All right. And also double check on what's going on. So we've got, do we have any zeros? I probably should mention that. Axis intercepts. Actually, before we draw it, we had to do axis intercepts. So let's do this first. Okay, axis intercepts. Okay, when x equals 0, y equals, well, I have a substituent here. X equals 0, okay, we have 8, so that's actually negative 6. Just that form's easy enough to do that. All right, and when y equals 0, use the format here, so we can just take that. 2x minus 6 equals 0. X equals 6 on 2 equals 3. There we go. All right, now let's draw it. Let's draw it over here. All right. Now, if you want, you can draw yourself a little sine diagram to go along with this. I might just move the camera a bit. All right. Why don't we use this as our sine diagram since I stuck it here anyway. So, all right, we've got 3, and we've got minus 1. All right, check your signs on those ones. So maybe if we go somewhere like negative 2, or maybe even negative 3. Negative 3 plus 1 is negative 2. 8 minus 8 divided by minus 2 is 4, and that is positive. Okay, between that, pick something like 0. All right, 0, well, we know that's negative because it's negative 6. And then something greater than that, maybe something like, let me pick 7. I'm just thinking of easy numbers to divide into this. 7 plus 1 is, 2 minus 1 is positive. Okay, so minus, positive, minus. So positive, negative, positive. Okay, anyway, look. And we have asymptote behavior. And I didn't have enough y space to put the negative 6, but maybe I'll just pretend that it's there. I won't do this to scale necessarily. All right, so we have, okay, minus 1. All right. Or maybe I'll pretend that's negative 6. I won't do the y to scale, so that can be 6. So let's do that. All right, and then it's going to, y is going to approach 2. So we have that horizontal asymptote. It's going to go through here. So we've got that side and we've got this side as well. All right, I think they do it better. They do a better job, but you got the general idea. That's how you go about doing these. Yep, and you can also check on your calculator by doing the graphs, but that's all right. I suggest you do that as well. So those are pretty easy enough. Let's move on. All right. So, all right. so let's move on to the next section, absolute value functions. Now, you've seen these in different contexts. I actually did a video for Specialist Maths in Stage 1. We looked at the absolute value function in terms of length of vectors. It's a very common operation. It has different contexts. In terms of real numbers, it basically, if you've got a negative, you return it as a positive. If you've got a positive, there is no change. So the absolute value function, so modulus x, there's a couple of ways you can express that. One is, you kind of write like this, it is minus x if x is less than 0, and it's x if x is greater than or equal to 0. So that's the sum of all values. So basically, if it's a negative value, you just you put a negative in front of it, and you turn it into a positive. So, or another way you can represent it, you can take the square of x and then take the square root. But essentially, if you think of this way is quicker. This way, we also do the same thing. So if you square a negative, you end up with a positive. You take the square root of that, it's still positive. The square root only returns the positive value by definition. So, all right. And the graph will look something like this. So if the graph of y equals modulus x is the linear graph, but the branch that on the other side is 0 will return the positive. So you can imagine that the graph is actually moving up this way through there, and the part that would have been negative of y equals x has now flipped over. In fact, it's a mirror on the x-axis. So the negative part mirrors onto the positive side of the x-axis. So like here. All right. So operations in terms of these. Yep. Okay. So basically, you can simplify and expand. I think this is all pretty straightforward. Maybe I'll go through another operation. So, all right. So maybe I'll do that. I'll do a question out of question 2 at least. I'll do a couple of these questions. All right. So 3F1. I'll do question 2D. All right. So if x equals minus 3, we'll find the modulus of this. 3 minus 2 lots of negative 3 minus negative 3 squared modulus. All right, so 3 plus 6 minus 9. Is there really much any more to it than that? No, well that's trivial anyway, because it's the modulus of 0, which is 0. Okay. Now be careful with something like this though. All right, so maybe I'll do B. 2B. 5 minus mod 3. Okay, so you return the positive there, but you've got a negative in front, so 5, well, I don't really need to write that out again. I'll just write it below. 5 take 3 is still 2 in that respect. All right. Whereas in part A, you would have 5 take negative 3, so that's 5 plus 3 is 8, and take the modulus is still 8. That's positive. All right. So, all right, some other operations. So from these, you actually kind of learn some of the patterns, and actually because we've actually already learned complex number version of the absolute value function, which you call the modulus. All these rules pretty much apply, so you're already familiar with that. Yep, if it works for complex numbers, it works for real numbers, so this is no surprise that modulus or absolute value function of A times B is equal to the absolute value function acting on A times the absolute value function acting on B. So, okay, maybe I will do something a bit more special. Let's have a look at question 6. All right, we'll do a couple of graphs. So, all right, write the following functions without absolute value functions, and hence write the equation. Okay, so if I was to take something like, okay, let's take 6F. I'm going to turn my light on, it's getting a bit dark in here. There we go. All right, so y minus 2 x. Okay, then we're going to break this up into two things, as they want to do. So in the case of when x is less than 0, well, then the modules, then this will be x minus 2, actually 2 times minus x, and then if it's positive or equal to 0, x minus 2x. So I'll simplify that to be, all right, so then the function is equal to, well, it's 3x on a domain of x greater less than 0, and it's actually minus x onto the domain of x is less than equal to 0. Let's see what that looks like. Okay, put my axis on. Okay, so for values less than x, it is 3x. So if I was to go back, all right, so if I go minus 1 would be minus 3. So let's go back. So minus 3, minus 3 in the y. Let's go down, minus 3 in the y, and then minus 6, and so on. So something like that. That's actually that part of the graph. And then we're at 0. So 0 is 0. And okay, for that is actually now down this way. So that's something to that effect. Let's double check if we've got that correct. I'm going to go to, you can use the graphics calculator, but for the sake of expediency, let's have a look at, sorry, I already had that up. Let's go to decimals. And you're welcome to, while you're learning these, to just fire up something like Desmos or use your graphics calculator and see if you've got this correct. So if I did x minus, and you can actually, in Desmos, you can type ABS, acting on x, and I forgot the 2. There you go. That's what we expected. Let's see, this one's going down, so like 1. 3, yep, minus 1, 3, and minus 2, 6, or thereabouts. Yep, there we go. And then this one's going down by 1 each time it goes across. Pretty much what we expected. Maybe let's take another one. Sure, show us our fluke. Please get back to my questions. All right, so maybe take something a bit more challenging. Let's take G. All right, 6G. All right, there we go. All right, 6G. Y equals plus 2 minus 2. All right. Well, let's have a look. That would be if, all right, so let's express that as, in terms of 2 parts, if x is less than 0, we have minus x, and then minus bracket x minus 2. And then it is, which actually simplified, or I'll write that on the next step. And then if it's positive, then we have x plus x minus 2. All right, so express it again, y can be expressed as equal to, okay, so we've got minus 2x plus 2 for the negative values. And then we've got 2x minus 2 for the positive values, or 0. So what does that look like? Well, let's take a look. Oh boy, I think I need more negative space. This seems to be a bit disjointed. I'm a little bit worried. Maybe I will test this first. Let's see what Desmos says. See this flat bit in the middle. I'm trying to make sense of that. No, actually, sorry. I'm completely mistaken. Of course it would be. All right, this would return values that it will switch them for values greater than 2. This section, I have to rewrite that entirely. That was completely wrong. All right, because this one will only trigger the sign change when x is less than 2. So we actually have 3 sections we have to think about. So let's rethink this one again. I was wrong. I had a feeling that wouldn't be right because I realized that would be a step function. It would basically just jump from one point to another if that was true. Let's rethink that. Okay, so all right, in terms of, let's break it up into 2 points. Let's break it up into what happens at 0, and then what happens also 0 and 2, or less than 0. What happens at less than 2, and then what happens after 2. Let's consider it this way. All right. All right, so if x is less than 0, well, let's have a look at that. So there's 3 parts we want. Let's start with what happens less than, so x is less than 0, but greater, no, let's go less than 0. That's right, that's the first one. The next part would be, okay, greater than 0, but less than 2, and then x is greater than or equal to 2. All right, so if x is less than 0, then this one will trigger the negative. So you have negative. Now, less than 0, this one is also negative. So this one's already triggered negative. All right, so then minus 2. Okay, so minus plus that. Something to that effect. So you've got the minus of that and minus of that because they're both in the negative range in terms of what's happening inside the absolute value functions. In the middle, now at this point, when x is greater than 0, this one is triggering positive, so that one's positive. Okay, so you don't need to swap the signs. This one is still between 0 and 2. This one's triggering negative, so you have minus x plus 2. All right, and then here, this is what's going to give us that little flat part in the middle. Okay, then when x is greater than 2, we actually trigger positive for that one, and we also trigger positive in this one. So yeah, that would be plus x plus, minus 2. So to simplify that, it's a function of x. It can be expressed as on these domains. All right, minus 2x plus 2 for x less than 0. Between 2 and 0 inclusive, it becomes 2. Then 2x minus 2 for x greater than 2. All right, so let's see how that works. So for x less than 0, so we can put in a value of something like minus 1. Well, it should start here, and then we go, well, we're going down. So if I actually put minus 1, so I get minus 1, I get 4. So don't actually need much negative space, fortunately. Let's go. Okay, that's 2, that's 4. Okay, so and then that's 8. So something like that. Okay, so there's that. That's at 2. Then for the next 2 units, it's 2. So like that. Then after that, we got 2x minus 2. So we're going up for 2 units every 1. So we're going to go up like that. Okay. And that's what you got. So that was a little more tricky. You have to stop thinking about zeros. You have to think about also what's going on here. So when does the part in the middle go to negatives is what you got to think about. If you've got more than one, you consider all the points where it swaps signs, and then that's where you get your reflections. So, okay. There we go. I don't need that one anymore. Okay. So, graph involving the absolute value function. Now, if you go and you graph, all right. So what if you were to apply the graph, the absolute value on the domain? Well, that basically just turns all your inputs positive if they were negative. So we discard the graph for greater less than 0 and reflect the graph on the y-axis. So basically, yeah, you get the copy what's on the the right hand side of the y-axis gets copied onto the left. All right. All right, but what happens when you put the absolute value function around that? Well, what that does is it any negative values output of the function will switch over to the positive side. So the negative parts will be a reflection on the x-axis. All right. So they've got an example here. So in terms of this graph, okay, so that's a quadratic. So the quadratic will be 3x squared minus 6x, but you can also use that value to the zeros. So you've got the zeros at 0 and 2. If you take the modulus of the input, then you get a reflection on the y-axis. You see here. So we've gone the graph back here, passes through 2, goes down, and then passes through 0. This is what it would look like here. We continue up like that, but instead we're mirroring on the y-axis. So you see this part here, because all those negative x values have now switched into the positive x values and put them through the function. They will have the same y values. So you have a mirror on the y-axis. So yeah, what was at -1, which is where the vertex is the same as what's at 1. And -2 is a 0, just like 2 is. And all the other points are copied up here as they are over here. So what happens in the other case? Put the modulus around the function, and the part that is below the x-axis gets mirrored above, like that. Okay, so you also, notice the absolute value function actually has very steep values in terms of changing the slope. So it's a bit of a tricky thing to do with calculus, because you say, what is the slope at 0, for example? But I'm not going to go through that because that's a rather advanced concept. You can see you switch from a negative to straight to a positive slope value as you go around the point of 2, for example, in here, and then what happens at 0 is a bit confusing as well. All right, but that's all right. We're not going to go through that, but it's an interesting point to bring up. So maybe we'll pick something a little bit more interesting. All right. So, all right. Maybe I'll go through. Nah, I think that's too much similar to the example. Let's do question 4. Let's pick a couple of these. All right. So, I'm going to pick question 4. We've already seen 2. Part 1's kind of trivial. Let's do 3 and 4. All right. So let's draw, why not? Let's draw the original function in. Okay, so we got that, we got that. So we've got 2, I haven't done this to scale, 2. So that's not the scale, obviously. All right, that's the function of x. So just going to do this roughly. What happens when I draw the same graph of, do I have to do both? No, just have to do the graph of that. Well, that's easy. What is negative is now positive, so that part goes up there, and that part goes up there. Goes across there. Just mirror on the x-axis. Okay. So if I drew over that in red, the red graph is now the modulus of fx. Easy does it. Similarly, that can make asymptotes a little bit more confusing. All right, and then I've got to do also for part A. Let's do part B as well. That actually you can do so we're doing for part B, repeat A, but this time draw the graphs of fx and f modulus of x. Yeah, so acting on that. What that would do, that would mirror the graph. So I would actually go down to 2. Yeah, I haven't done this scale, unfortunately. But it'll go up, so just mirror on the other side. Maybe I should actually just draw that separately. Okay. So if I call that as 2, let's do it on the same side, that's -2. And I have a cubic, goes for 0, goes for 2, finishes up. All right, then what does it look like? So that's that is the function of x, like that. What does the function of that look like? Well, it is the same here, so I can just kind of draw over that in green. You can't see the green too well, but I'll fill that out. So it does that. Now it goes through 0, and then basically it's going to do the same thing on mirror of the y-axis. So you're going to get this kind of graph. All right. Should I do 4? All right, why not? All right. Let's draw it nice and big. Do I have? No, I don't. Why not? I don't know. Oh boy. Doesn't matter. All right. Draw it nice and big. The last one we're going to be doing. Okay. All right. All right, so we've got this part. So we've got this sort of function. It goes through 0. Oopsies. Fell into a hole. There we go. All right. We've got y equals 2. We have x equals 4. That's those asymptotes, and it passes through 0. Right. So what does it look like if I was to do, so that was a graph of f of x. All right. What does the modulus look like? Well, everything that is negative must be reflected positive. So strange as it is, this graph would be the same here. Then it's going to go whoop, do the opposite. And that's it. And then the rest of it would actually be the same. So it just mirrors on the x-axis. So it looks strange that it's cutting the horizontal asymptote, but that's what it is. All right, so that's f modulus x. So modulus of f of x, I should say, versus the f modulus x, which is, I'm going to draw that in green. Okay, oopsies. That'll be a different graph entirely for the modulus outside and inside. What does that look like? Well, that's a mirror on the y-axis. So all these negative values, they're going to return what's said in the positive values. So you're going to end up with a graph doing. So maybe we'll put a green asymptote because it will have asymptotic behavior there. It's going to go down like that. And then it's going to come up through here, like it mirrors on the other side. And then the rest of it's the same. So then that part's also green. So that's green as well. There you go. You can try it for yourself. But that is the end of the chapter. We're not going to go through the extension stuff. Don't have to worry about all those positives and negatives floating around everywhere. So that's all we're going to cover as far as chapter 3. So you can start the review set yourself. That's all I'm going to cover though. So see you in the next video.